The universe is full of mysteries. It keeps secrets well. For many decades, we have been staring at one of its biggest puzzles. We see its effects everywhere we look in the cosmos. It pulls on stars. It shapes entire galaxies. It bends the very fabric of space-time. Yet we cannot see it. We cannot touch it. It remains a ghost in the cosmic machine. We call this mystery dark matter. Now, as of November 2025, a new claim has sent ripples through the scientific community. A team of dedicated scientists working in the quiet, dark deep beneath the Earth may have just detected the first faint whisper from this invisible realm. It is a moment filled with both exhilarating hope and profound caution. For as long as we have pointed our telescopes to the sky, we have been cataloging what we can see. Stars, planets, nebulae, galaxies. They are made of the same stuff we are. Protons, neutrons, electrons. We call this normal matter, but the math does not add up. The universe behaves as if there is much more mass than we can account for with our eyes and instruments. This missing mass, this dark matter, makes up about 85% of all matter in the cosmos. That means the universe we know, the one that glows and shines, is just the tip of the cosmic iceberg. Finding dark matter is not just about checking a box. It is about understanding the fundamental architecture of reality itself. This new potential discovery is not a loud announcement. Instead, it is a subtle hint. It is a statistical anomaly in a sea of data. A tiny bump on a graph where there should be a flat line. But in the patient and meticulous world of particle physics, a hint like this is electrifying. It is a breadcrumb trail that could lead us out of the dark and into a new understanding of the universe. It represents the culmination of decades of effort, of building ever more sensitive detectors, and of waiting patiently for a signal from the great unknown. The journey to confirm this finding will be long and arduous, but the first potential step has been taken. The implications are staggering. If this signal is confirmed to be dark matter, it will be one of the most significant discoveries in the history of science. It would be on par with discovering the atom or understanding gravity. We would finally have a tangible piece of the puzzle that governs the structure and evolution of everything. It would open a new window onto the cosmos, revealing a hidden landscape that has been shaping our reality all along. So, what exactly is this dark matter that has scientists so captivated? Dark matter is matter that has mass and therefore gravity but does not interact with light. It does not emit, absorb, reflect, scatter. This is why we call it dark. It is utterly invisible to our eyes and our most powerful telescopes. It is a cosmic ghost passing through us and our planet every second without leaving a trace. We only know it exists because we can see its gravitational influence on visible stuff. It is the unseen puppeteer pulling the strings of the cosmic ballet. Outer stars move just as fast as inner ones. The simplest explanation is a massive, invisible halo around the galaxy, providing extra gravity to hold those speedy stars in orbit. Second, gravitational lensing, even more dramatic. Massive objects bend spacetime. A galaxy cluster can act like a giant magnifying glass. It bends and distorts light from more distant objects. By measuring the bending, astronomers calculate the lens mass. Repeatedly, that mass is far greater than visible stars and gas. That missing mass is dark matter. What could it be made of? Leading idea, a new subatomic particle, often called a WIMP, weakly interacting massive particle. Massive, enough mass to explain the gravity. Weakly interacting, it almost never bumps into normal matter. How do you catch a ghost? How do you detect a particle that barely interacts with anything? The search for dark matter is one of the most challenging and ingenious endeavors in modern science. Scientists are using a three-pronged approach. They look up to the heavens, they look down into the earth, they try to create it themselves. The first method involves astronomy. By observing the movements of stars, by observing the lensing of light, by observing the cosmic microwave background radiation. This tells us about its role in the universe's evolution. The second, and most relevant for our current story, is direct detection. Scientists try to observe a dark matter particle directly interacting with a detector on Earth. They build incredibly sensitive instruments and place them deep underground, housed in old mines, housed in tunnels through mountains, housed in specialized subterranean labs, deep underground to shield from cosmic rays and other particles. Several kilometers of rock act as a natural filter, stopping almost everything except neutrinos and, hopefully, dark matter. These detectors are marvels of engineering. Large tank of super pure liquid xenon. Large tank of super pure liquid argon. Tanks cooled to extremely low temperatures. If a dark matter particle collides with a nucleus, it creates a tiny flash or burst of energy. Highly sensitive sensors surrounding the tank pick up that minuscule signal. The challenge is immense. Expected interactions, only a few events per year in detectors with tons of material. Scientists must meticulously account for all other possible sources of similar signals. The third approach, create dark matter in the lab. Giant particle accelerators, like the Large Hadron Collider at CERN, smashing protons at nearly the speed of light, recreates early universe conditions. Dark matter wouldn't show up directly in detectors. Instead, scientists look for missing energy and missing momentum in the collision debris. Each method provides a way to cross-check and verify a potential discovery. Now we arrive at the heart of the current excitement. A team of scientists working on one of these deep underground direct detection experiments has announced a new and unexpected result. After painstakingly analyzing years of data, they have found a small but statistically significant excess of events. This means they recorded more interactions in their detector than they can explain with all the known background sources. These background sources are the usual suspects. Trace amounts of radioactive elements in the detector materials, stray neutrons, neutrinos from the sun. The team has spent years modeling and measuring these backgrounds with extreme precision. The signal itself is not a loud, unambiguous discovery. It is more like a faint pattern emerging from the noise. The excess events are clustered in a specific low-energy range. This is important because many theoretical models of dark matter predict that interactions would indeed produce signals in this very energy window. The characteristics of the observed events, how the energy was deposited in the detector, are consistent with some of the leading candidates for dark matter particles. It is this tantalizing correspondence between the unexpected data and the theoretical predictions that has captured the attention of the physics world. It is the first time a signal this clean has appeared in just the right place. The research team behind the finding has been exceptionally careful in their announcement. They are not claiming to have discovered dark matter. Instead, they are presenting their data to the wider scientific community and stating that they have an anomaly they cannot explain. This is the scientific method in its purest form. They have ruled out every known explanation they can think of. Now they are asking for help. They are inviting other experts to scrutinize their analysis, to challenge their assumptions, to search for alternative explanations that they might have missed. This public and transparent process is crucial for building confidence in any scientific result, especially one of this magnitude. So what did the experiment actually find? Without getting too deep into the technical details, the detector recorded a handful more tiny flashes of light than expected from background processes. While a handful may not sound like much in the world of particle physics, where every single event is precious, it is enough to make everyone sit up and take notice. The signal is strong enough that the probability of it being a random statistical fluctuation is very low, though not yet low enough to meet the rigorous 5 sigma standard required to claim a formal discovery. It is a compelling hint, a whisper from the dark. In science, especially when dealing with a potential discovery of this scale, excitement is always tempered with a healthy dose of skepticism. The history of physics is littered with promising signals that turned out to be false alarms. These discoveries vanished upon closer inspection. Sometimes the cause was a subtle, unforeseen effect within the instrument itself. Other times, it was a previously unknown background source that mimicked the signal of new physics. This is why the community's reaction to this new dark matter hint is one of cautious optimism. Everyone is thrilled by the possibility, but no one is ready to celebrate just yet. The burden of proof is extraordinarily high. The first step in the verification process is intense scrutiny of the experiment that made the claim. The team's data analysis will be picked apart by experts from around the globe. Did they correctly model all the background radiation? Could there be a tiny contamination of a radioactive isotope in their detector material that they did not account for? Is there a flaw in their software? Is there a subtle calibration issue with their sensors? This is not about distrusting the original team. It is about recognizing that these experiments are so complex that even the most brilliant scientists can miss something. This peer review process is a cornerstone of scientific progress, ensuring that results are robust and reliable. The single most important step, however, is replication. A discovery made by one experiment is just a hint. A discovery made by 2 or 3 independent experiments becomes a fact. There are several other dark matter detectors operating around the world. They use different technologies. They use different target materials. Scientists at these other facilities will now be racing to check if they see a similar excess of events in the same energy range. If another experiment, perhaps one using liquid argon, sees the same bump in their data, the case for dark matter will become dramatically stronger. If another experiment using liquid xenon sees the same bump in their data, the case for dark matter will become dramatically stronger. If they see nothing, it could mean the original signal was a fluke or an artifact of that specific detector. This process of cross-checking can take years. The experiments need to collect enough data to have the statistical power to either confirm or refute the signal. In the meantime, theoretical physicists will be working overtime. They will be trying to figure out precisely what kind of dark matter particle could produce the observed signal. Does it fit neatly into existing models, or does it require new and exotic theories? They will also be looking for other ways to test the hypothesis. For example, it might also produce a faint gamma-ray signal from the center of our galaxy. Astronomers can then point their telescopes to see if that corresponding signal is there. Let's allow ourselves a moment to dream. Let's imagine the coming years of scrutiny and replication confirm this signal is real. What would it mean? Discovery of a dark matter particle. It would change our understanding of the universe. For nearly a century, cosmology had a giant hole labeled dark matter. Finding the particle would finally fill that hole. We would move from knowing dark matter exists to knowing what it is. A monumental leap, an entirely new field, dark matter physics. A new piece of the cosmic puzzle to study. A cascade of new questions and new avenues of research. What is the exact mass of this particle? How does it interact with other particles, if at all? Is there just one kind of dark matter particle? Or is there a whole dark sector with its own particles and forces? Answering these needs a new generation of experiments to study properties in detail. Particle accelerators retasked to produce these particles in large numbers. Profound implications for cosmology and astrophysics. Our galaxy formation theories rest on a dark matter scaffold. With a known particle, we could refine these models with incredible precision. We could run simulations based on measured particle properties, not placeholders. That would reveal the history and future of the cosmos more clearly. It could explain the detailed structure of galaxy clusters and the fine-grained texture of the cosmic web across the universe. A triumph of human curiosity and ingenuity. The scientific method, making predictions, building difficult experiments to test them, patiently sifting through mountains of data for a tiny signal. Proof we can probe the deepest mysteries, even those hidden from sight. A source of inspiration. We still have so much to learn about our cosmic home. The universe would seem a little less dark and a lot more interesting. Yeah, it's a tough hunt. In summary, the universe may have just given us a vital clue. In one of its longest-running mysteries, scientists searching for the elusive dark matter have found a signal they cannot explain with our current physics. This is not a confirmed discovery, but it is the most tantalizing hint we have ever had. A glimmer of light in a search conducted in the dark for decades. The mood, excited anticipation, and a deep understanding the hardest work is still ahead. From glimmer to beacon will be long and demand immense scientific rigor, immediate future, independent verification. Other experiments must search their own data. If the signal persists across detectors and across techniques, confidence will grow exponentially. Meanwhile, the original team and outside experts will exhaustively search for mundane explanations. Science self-corrects by relentlessly questioning results. We ensure any announced discovery rests on the most solid foundation. See science in action. It's not a straight line from question to answer. It's a messy, exciting, deeply human process of exploration, pushing boundaries of technology and of knowledge into uncharted territory. Stay curious. Follow scientific collaborations and trusted science communicators. Uncertainty isn't weakness, it's part of discovery. Small hints matter, even if they don't pan out. They guide research. They build better experiments. They narrow the universe's hiding places. The hunt for dark matter. Marathon, not a sprint. This signal might be the first glimpse of the finish line, or a mirage on the horizon. Either way, we learn more about the cosmos, building detectors with unprecedented sensitivity and pushing technological limits. Hint, Nobel Prize, or hint, footnote. Either way, knowledge advances. The mystery of dark matter is not solved yet. But for the first time in a long time, it feels like we might be getting closer to turning on the lights. And that is a truly cosmic thought. The story is just beginning. The chase continues.